We learned a conversion factor between volume and moles last class. Okay, volume and moles at STP specifically, right? Go back to your notes and figure out what's the conversion factor. How many liters are contained in 1 mole of any? Yep, how much is it?
22.4 liters.
22.4 liters. And so that conversion factor allows us to make our stoichiometry a little easier, really, right? 1 mole of any gas, 1 mole is equal to 22.4 liters. But the caveat is that it has to be at STP. It has to be at STP. If our reaction is not at STP, we still are probably going to do a stoichiometry problem, but we're going to have to do an ideal gas law problem to go with it, right? We're going to have to put our other conditions and figure out how many moles of my gas then do I have. If I don't have 22.4 moles, because I'm not at STP, then 22.4 liters, then I got to figure out really what is my volume or what is my whatever, and then I can go from there. Okay, so sometimes we're going to have just a quick stoichiometry, and sometimes we'll combine stoichiometry and the ideal gas law. So let's just start on this first problem here. It says, how many grams of aluminum oxide are formed from 15 liters of O2 at STP? Okay, this is just a regular stoichiometry problem. Luckily, not yet a limiting reactant problem, right? It's just a starting amount and a finishing amount. So my goal here is to find out how many grams of aluminum oxide if I start with 15 liters of O2. All right, 15 liters of O2, but I want to get to grams of aluminum oxide. And we said our special set works if it's at STP. So I'm going to be able to figure out how many liters of O2 will tell me how many moles of O2 I have. So I'm going to start my T-chart always with what I know, 15 liters of O2. And instead of going grams to moles like we always do, we're just going to go liters to moles, right? And we know that 1 liter of O2 is, 22.4 liters of O2 is equal to 1 mole. Right? This is our conversion factor that we just learned. Okay, so 1 mole of O2. And then from there, it's just a regular stoichiometry problem. So we're going to go moles of O2 to then what? Do you remember how it works here? What's this next step called? Mole ratio step. Good, mole ratio step. So I'm going to go from moles of O2 to moles of aluminum oxide. And these numbers come directly from our balanced chemical reaction. So O2 gets a 3, and aluminum oxide is going to get a 2. And then I'll finish my problem with moles of aluminum oxide and grams of aluminum oxide. Okay, because it asks me for grams. Here, moles goes back to getting the 1, and I need the molar mass of aluminum oxide, 102 grams. Okay, and so that gives me 102 grams. All right, 22.4 works because I'm at STP. Let's see here. I started with less than 1 mole of oxygen, so that gives us a little bit of an idea of what our answer, kind of gives us a range about what our answer could be. Did we get about 45? Mm-hmm. Yes or no? Yep. Sorry, okay. Al2O3. Next one says, how many liters of water can be made from 6 grams of hydrogen gas at STP? Okay, so again, we're at STP. That tells me I can use that 22.4 conversion factor. But this time I'm starting with 6 grams, and I want to know how many liters of water can I make. Okay, so I just start with what I know. I'm going to get rid of grams of H2 and go to moles of H2. Moles of H2 to moles of water. That's our mole ratio step. And then moles of water. What am I aiming for here? What am I going to go to up there? I'm going to go to liters of water. All right, so my molar mass for hydrogen, remember, is not just 1, it's 2 because it's hydrogen gas. This is going to come directly from our mole ratio. And 1 mole is equal to 22.4 liters, right? That's one that's going to be given. And it's like Avogadro's number in the way that it doesn't matter what molecule this is, right? As long as it's at STP, 1 mole to 22.4 liters is constant for every molecule. Okay, so it's like Avogadro's number in that way. Okay? All right, we started... we should have an idea of what our range is going to be. Is that about what we had? 44.8 liters of water? Is that not what you had? No? Okay. Do your numbers look like mine?
My numbers are the exact same.
Oh, I divided by 3, not by 2. Okay. All right, let's try that again. How about 67.2?
Yep.
There we go. Thank you. All right, liters of water. It says how many liters of chlorine will be needed to make 75 grams of C2H2Cl4. Assume 1 atmosphere of pressure and 298 Kelvin. So is 298 Kelvin, is that STP?
No.
It's not. So we can't just use our basic conversion. So I want you to brainstorm here. How can we make that work? How do you think we could get there? Yeah. Convert it to STP. If we would convert these to STP, we would also have to make a change about our starting amount too. Okay?
Ooh. Just calculate liters for that given situation.
Calculate liters for that given situation. Good. But what do you... I can't calculate... you want me to calculate liters of my starting amount or liters of my product?
Liters of chlorine.
Liters of chlorine.
No, hold on.
Okay, how can I do that?
There's 1 mole.
Can you use the ideal gas law?
We're going to use the ideal gas law, yes. But I'm going to recommend that we use it last. So here's what we can do. We know that we're going to have 75 grams of this, but our goal is to find out liters of chlorine. What we can do is stoichiometry to moles of that substance, then plug it into the ideal gas law. Right? I can find out how many moles of Cl2 I need, and then I can go ideal gas law because I'll have pressure, temperature, I'll have the number of moles, I have R, and then I can solve for what volume that amount of moles will take up under those conditions. Does that kind of make sense? All right, so we're going to go stoichiometry here with 75 grams. C2H2Cl4. I'm going to get rid of that and go to moles. About 170, is that the molar mass you came up with? No, man, I'm having trouble today. 168, okay, all right. What'd you use for chlorine?
35 plus 5.
Okay.
I got 167.6.
168. Let's do that. 168 to moles. Then I'm going to keep going, and I'm going to get rid of moles of C2H2Cl4 and go to moles of just Cl2. And that's where I stop, right? I want to stop right there because I just want to find out how many moles, what substance of chlorine, right? What's my quantity of chlorine that I can have? So this is going to be 1 to 2. And I'll find out how many moles of chlorine I need to produce that. 75 times 2 divided by 168. I don't even want to say what I got because I've been wrong so many times today, but 0.893. Oh, there we go. Moles of Cl2. And so that tells me with my reaction, right, if I want to produce 75 grams, I need to start with 0.893 moles of Cl2. And so, yeah, now we've got to figure out how much volume is that. And I can't just take that times 22.4 because I'm not at STP. So I'm going to take that amount, and we're going to use the ideal gas law. PV equals nRT. My pressure, we already said, was 1 atmosphere. Volume is going to be what we're solving for. 0.893 is my moles. What's my R value always? Yep. 0.0821 and then 298. So I'm going to solve here for my volume. And we get a value of 21.84 liters. All right. Now I want you to see, do you feel like that fits within an expected range? Right? I don't have a range for you necessarily, but just think about this. If 1 mole of substance at STP has a volume of 22.4, how far off are we from STP? 25 degrees, right? Not that far. Our pressure's 1, temperature's 25, so we're not too far off. And how far off are we from 1 mole, right? Not that far. So I think it should make sense to us that this number is within the range of our STP value. If this amount of moles were at STP would have been 20.0. Okay, so we're pretty close. But that's it. That's gas stoichiometry. Simple enough, right? You're going to have to maybe do multi-step, right? I'm going to have to ask you to do multi-step. So problem solve your way through these a little bit, right? Figure out what can I solve for to get to my final product, okay? And there's not always one path to the right answer. There might be multiple ways you can get to the right answer, and that's okay, right? The way you solve it might not be exactly the way I solve it, as long as we end up working it out the same, okay?